So I can say that this is the same as G. This is same as G to the P less than or equal to 1. Why this will be the case? Here's the thing. Have I defined G? Where have I defined G?
Define.
Okay, so I missed one thing. By the way, here G is the name given to this limit. G is this limit. So if this G is the limit, then it must be same as the limit. Okay. I can say that this is less than or equal to. So what does this shows? So this shows that the pth norm of G is also less than or equal to 1. It is strictly less than or equal. Okay. By the way, can I conclude from here? So if the pth norm of G is less than or equal to 1 and hence finite, then can I conclude from here that G of x, whatever it is, it must be finite almost everywhere. In other words, you can't have a G of x that is infinity and giving you its norm less than or equal to 1. This is not going to happen. Okay. This must be true. Okay. So if the G of x is infinity, you can't have this. So you have a choice. If this is true, then this guy must be finite. Almost every. Not saying that. So let's have a quick overview that what we have done. So we started with a Cauchy sequence. We said there is a subsequence which behaves like this. Then I'm considering the partial sums, and I gave its limit a name G, which is not necessarily finite at the moment. Okay. And so by Minkowski inequality, this must be true, and so this must be true, and by Farou's lemma, this must be true, and these two guys are same. So inequality, this inequality should hold. And what does this mean is that the p norm of the G must be less than or equal to 1, and therefore the G must be of less than finite almost everywhere. Now here is the thing. What is G? It's a limit of the partial sum, and hence it's a series actually. So what you are saying that this series is finite almost everywhere. So what does this mean? That this series converges? At least absolutely almost everywhere.
The series conversion.
Almost everywhere. Okay? That's what it shows. Okay. So this thing must be controllable quantity. Shall I write a few things down? So my essential focus is going to be to construct a net which I can treat as the limit of this sequence, this subsequence, and then I'll show that the function would also converge to the same. The old classical trick. So in other words, you want to, show a Cauchy sequence convergent, take a subsequence, show it is converging to something, then the Cauchy sequence would also converge to that. Okay. Now, let me define a function f actually. So f is that function which I can treat as the limit of my Cauchy sequence that I'm interested So f is what? So f of x is this time. And 1 of x plus I equal to 1 to infinity f and I plus 1 of x minus f and I of x. Is it making, can you see that? If you can't see it, let me write there. Make sure that yes. This is coming okay? Yes. Because I can see a shadow. So let me define a function and see the trick. So the f of x is basically, so in other words, I know that the series that I have defined by G is convergent almost everywhere, right? So whenever it converges, I'm giving that series this name actually f. So in other words, f of x is fn of x plus I equal to 1 to infinity and I plus 1 of x minus f and x, etc. Obviously, it's p plus no. P without absolute action. Okay. So this is equal to this series where this series converges, okay, and it's equal to 0 where it doesn't. Otherwise, ठीक है.
क्लियर करेंगे ये लिमिट है.
Sorry?
ये लिमिट क्लियर.
Yes. And I know that like, this converges absolutely almost everywhere. Why absolutely? Because that thing is absolute action. This converges almost absolutely everywhere. Absolute convergence implies convergence. Okay, so this convergence almost everywhere. So wherever it converges, give it a name f of x. Where it doesn't, so in other words, by wherever I mean what precisely? For those x for which this is converging absolutely, for such x, I am giving f of x a name h, which is basically the limit of it. And if this guy is not converging for some x, then I am assigning f of x 0 for those values. Okay. Now, so previously we considered the partial sums of absolute of this series, so now consider the partial sum of this series. So consider this partial sum, fn 1 of x plus I equal to 1 to k, fn I plus 1 of x minus fn I of x. Okay? What would be the ultimate outcome? So that's a telescopic sum actually. Okay, without absolute, that's a telescopic sum. So the term that is going to survive is the last term. This is equal to fn k of x. First term. Fn k, okay. The first term would be, so here's the thing. So if you substitute I equal to 1, so you'll have fn2 minus fn1, but this fn1 will be cancelled with fn1. You have this term here. Don't forget. Okay. And so what does this mean? So if I take limit on the both sides of this guy, this what you call k goes to infinity on both, what does that mean? So I'm going to say that limit n goes to infinity, fnk of x, okay, is going to be this limit of this. So you're going to have a 1 to infinity, but this is equal to, isn't that equal to f of x actually? Okay, so it is 1 to infinity, and wherever it converges, that is equal to f of x. So if I take the limit on the both sides, k goes to infinity on here, so you can get f of x. But I know that this is not true at all points, it's just true almost everywhere, so this must be true almost everywhere as well. Okay. So what does this show? What does this mean? This means that the subsequence that you took, okay, is converging almost everywhere to this function that you have defined up. Now since, point, I will first explicitly write it. Since this sequence fnk of x, okay, which is this fn1 of x plus some I equal to 1 to k, fni plus 1 of x minus fni of x, okay, and it's absolute. I can show that this is less than or equal to, say, a fixed function g of x. So using my previous calculation, g of x, okay, not that without absolute g of x. So this means that this sequence is dominated by g of x, and it's converging almost everywhere to f of x. So then, by the dominated convergence theorem, what follows are the results that we have followed, that this f and k converges to f
in LP sense.
in LP sense. Almost done. So see, what is the key trick in this proof? The key trick in this proof is that you took a sequence and took a Cauchy sequence, and you showed that in that Cauchy sequence there is a convergent subsequence sitting actually, and that convergent subsequence is converging to some f. Then what I would like to show essentially that the sequence is also convergent. It's the same value. That's what is basically my key contention. Okay. And now I will also use explicitly the Cauchiness of the sequence. So there I use implicitly the Cauchiness of the sequence, but now probably you have this. Further I've gone here. Thinking the first time about all this, you must be all well. Okay, so let's get to flow. So now suppose someone has given me epsilon and said me to prove that your Cauchy sequence that you have been given is going to converge to the same f in LP sense. Okay. Now, I don't know that whether Fn, the sequence that is Cauchy sequence, is going to converge to f or not, but I know that it's a Cauchy sequence, so I can say for this epsilon, I can find a capital N such that after this n, Okay. This difference is less than epsilon. And now I want to do what? I want to somehow insert f in between. But cleverly. It's not going to be as straightforward as it seems, but yes, that's what I would like to show. So now consider this. So f minus fm is consider this. F minus fm is by the way, can I say, since f is the limit of this sequence actually, Cauchy sequence, that subsequence. So can I say this is same as the limit, so I took the limit for this, limit of fnk minus fm is, should be okay. Should be okay. You know why this is the case? Because f and k converges to f almost. And now if I integrate this guy, f minus fm is p. So I need to integrate this side. Okay, so limits fn k minus fm is to p, and I can do what? I can pull this limit out, and I'm going to have fn k minus fm is p, right? And what would be this guy? Can you give me an estimate of this number? The last number? This must be. So fn minus fm is what?
Less than epsilon.
Is less than epsilon for all and you know and what do we call and bigger than or equal to capital N. Eventually you're gonna have a k for which you can say that this is less than epsilon over here. Okay. This is less than epsilon over here. Almost done. Okay. This implies that f minus fn is less than, what do you say, epsilon. Okay. So by the way, what does this mean that fm converges to? Fm converges to f in LP sense. The only thing that remains now is that f is necessarily in LP actually. Okay, it's converging to f in LP sense. But is it necessary that f must be a part of the LP space? So what you need to do, you need to compute the LP norm of f and we need to show that. But I can do it easily. Okay. So let's add and subtract fms. Okay. Costy, triangle inequality plus fp. Okay. And I can play around with, this is less than epsilon. I can play around with this term in such a way that, by the way, I don't need to show that this is less than epsilon, I just need to show that this is finite. So this is indeed finite. Why? Because less than epsilon and these guys are from LP actually. So this is finite. Okay. So that is n indeed LP mu. Okay. By the way, what we have proved, I don't know whether I mentioned it or not. So
Every Kashi is convergent.
here's the thing. Every Cauchy sequence is convergent, so therefore LP of mu is Banach. But one thing is that is remaining is this actually. That this is true for, the argument is true for between P1 and less than infinity. Why? Because you can't put a power infinity. Okay? So, but our claim was in our theorem field, the Riesz-Fischer theorem, is that L infinity is also a Banach space. So, in other words, you have to consider L infinity separately. So, that's a very easy proof actually.
सर जब सूट लेवल की बात जो आपने कंटिन्यू किया है स्टार्ट
Yeah. So see, I mean, if you see the limit of these GKs, we named them G actually. The limit must be
सही
Okay, so now let's quickly prove this actually, that this is Banach. This is easy actually, it's not straightforward. Because obviously, with this integral definition, you can't put p equal to infinity in power actually. This only works when the p is finite. Okay, but the claim was that LP is Banach for all values between 1 to infinity, including infinity. Okay.